Imagine writing a relatively simple piece of code. You hit run, and instead of just executing your commands top to bottom, the code begins to mathematically prove its own logic.
Right, which is already kind of mind-bending.
Exactly. It rewrites its own execution paths, and eventually it transforms itself into a literal neural network. And today, we're not talking about a sci-fi movie.
No, we are definitely not.
We're doing a custom-tailored deep dive just for you into a massive documentation repository. It's for a programming language and ecosystem called Eshkol. And let me tell you right up front, this completely breaks the paradigm of what a programming language is supposed to be.
It really does. I mean, usually the relationship we have with our tools is totally static, right? You pick up Python or C++, you give it a command and the machine obeys. The boundaries are clear.
Yeah, the wrench doesn't redesign the engine while you're holding it.
Exactly. But Eshkol is actively trying to, well, collapse the distance between the language, the compiler, and the artificial intelligence itself.
Which is just wild to think about. So our mission today is to help you navigate this incredibly dense, ambitious technical landscape. We're going to extract the core architecture, figure out how it handles these crazy AI and math capabilities, and explore the testing frameworks that keep it all together.
And we'll do our best to do it without getting bogged down in the actual code level syntax, because it gets complicated fast.
Seriously. But it's a fascinating journey because it starts with such a classical pedigree, you know? If you look at the documentation, the foundation of Eshkol is scheme compatible.
Yeah, specifically, it boasts R7RS compliance.
Right, so let's establish a baseline there. Scheme is a dialect of Lisp. It's historically known for being incredibly minimalist, pure, and mostly beloved by academics.
Pure functional programming.
Exactly. But Eshkol has taken that minimalist foundation and absolutely supersized it. The documentation lists over 555 built-in functions.
And 58 standard library modules containing 638 symbols.
Which is your first massive clue that we aren't just dealing with a simple scripting tool here.
No, not at all. I mean, they've retained the elegance of scheme things like powerful macros that let you invent new syntax, but they've bolted on an industrial-grade engine underneath.
Yeah, the Getting Started section really captures this whiplash. They have a 15-minute quick start guide, right? And it casually promises to take you from basic concepts like closures straight into tensors and gradients.
In 15 minutes.
Yeah. It feels a bit like walking into your neighborhood hardware store to buy a simple claw hammer and realizing that aisle 3 is stocking aerospace engineering equipment.
And orbital thrusters, yeah, it's a completely jarring shift, but it raises a really fundamental architectural question.
Which is?
Well, why build a language that spans from simple text macros all the way up to tensor calculus? I mean, why not just do what Python does?
Oh, right. Like you write in a simple language, and when you need heavy math, you import a library like NumPy to handle the tensors.
Exactly. Why bake all that complex math directly into the core specification of the language?
Well, it comes down to how compilers optimize code, right?
Yeah.
When you use an external library, the compiler sees a black box. It hands data to the library, waits, and gets data back.
So it can't optimize the internal steps of the math.
Precisely. It's totally blind to it. But in Eshkol, the numeric tower, which handles everything from simple fractions to massive exact numbers, is native. The tensor operations are native.
Which means the compiler intuitively understands the math you are trying to do.
Exactly. Because it has full visibility, it can optimize the memory allocation and the execution path across boundaries that a standard library simply can't cross.
So the language doesn't just calculate numbers, it actually understands the mathematical concepts behind them.
Right.
And that is what unlocks Eshkol's machine learning capabilities, specifically automatic differentiation, or AD.
Yeah, the documentation notes over 75 machine learning built-ins, but AD is clearly the pillar holding this all up.
Absolutely. Now, when we talk about automatic differentiation, we should clarify for you listening, we aren't talking about numerical estimation here. No, it's not the computer drawing a tiny line on a graph to guess a slope. It is the exact step-by-step calculation of derivatives directly through your code.
And Eshkol uses what they call a Taylor tower design, right? To support arbitrary order AD.
Yes. They mention a forward jet and a reverse tape system for this.
Okay, so how does that actually work in practice?
Think of it like keeping a perfect receipt of every single mathematical operation. In the forward jet mode, as the program calculates a value, it simultaneously carries forward the exact derivative of that value.
So they travel together like a pair through the program.
Exactly. Now the reverse tape mode does the opposite. It executes the whole program, records every single operation on a literal digital tape, and then plays it backwards.
To trace the derivatives from the output back to the input.
Right, and Eshkol can even mix these modes dynamically depending on what's most efficient.
Okay, that makes sense for calculating a first derivative, or, even a second derivative for things like acceleration. But you mentioned arbitrary order AD.
Yeah, infinite layers of differentiation.
Right. I have to ask, why on earth would anyone need to calculate the 5th, 10th, or 100th derivative of a function?
For everyday coding, you wouldn't at all.
Yeah, I didn't think so.
But Eshkol is built for deep scientific computing. Think about meta-learning, where an AI model is trying to optimize the optimizer that is training another AI model.
Oh, wow. Okay, turtles all the way down.
Pretty much. Or think of complex dynamic systems like fluid dynamics, chaotic weather patterns, or orbital mechanics.
You need those deep, arbitrary layers of calculus to accurately model systems that are just constantly shifting.
Exactly. And Eshkol's compiler uses an AD oracle matrix to track all the capture rules so scientists can nest these derivatives endlessly without the system just, crashing.
But wait, if you're calculating infinite layers of calculus and carrying perfect receipts of every single operation, A traditional CPU interpreter would completely choke.
Oh, instantly, it would grind to a halt.
Right, so the language would be practically unusable unless the engine itself is fundamentally redesigned to handle that kind of math.
Which is exactly why the runtime engine is an absolute beast. It starts with a 64 opcode core interpreter that runs their custom binary format, the ESKB format.
But the real heavy lifting is done by a JIT, right? A just-in-time compiler.
Yeah, powered by LLVM or JIT, according to the docs.
So it's taking this high-level, complex math and compiling it down to raw machine code on the fly exactly when it needs it.
Yes, and it's incredibly hardware aware. Like, it features a cost model threshold for GPU dispatch.
Okay, break that down for me.
Well, usually moving data from the CPU over to the graphics card takes time. If a calculation is too small, the round trip to the GPU actually slows you down.
Oh, right. The overhead of moving the data is worse than just doing the math slowly.
Exactly. So Eshkol's runtime calculates that threshold on the fly.
So it looks at a math problem and decides, no, this is too small for the GPU, keep it on the CPU.
Right, or it says, this is massive, send it to the NVIDIA chip.
That is brilliant. It dynamically offloads to Metal on Apple devices, CUDA on NVIDIA, or XLA backends, right?
Yep. It even has native support for specialized embedded hardware, like the Jetson AGX Xavier.
That dynamic hardware routing is super smart.
Yeah.
But here is where the engine room documentation gets genuinely mind-bending.
Oh, yeah. The VM memory ops.
Yes. Deep in the architecture notes, there are references to a computable transformer and VM memory ops as weight matrices.
This is the exact moment Eshkol crosses from being a standard programming language into being an autonomous entity.
Right, because the documentation states that Eshkol can encode its own programs as neural network weight matrices.
Specifically, it uses a 6-layer transformer virtual machine encoding.
So if I'm understanding the mechanics here, it's not just a program processing data through an AI. The code is literally turning its own instructions into a brain to execute faster.
That is precisely what is happening. In a normal virtual machine, the program reads an instruction like, add these two numbers, and executes it.
Basic step-by-step logic.
Right. But in Eshkol, that sequence of operations can be fed into a transformer model. The weights of that neural network mathematically represent the program itself.
That is wild.
The execution of your code is literally just a forward pass of the neural network.
It's like writing down a recipe for a cake on an index card, and the index card spontaneously folds itself into an oven to bake the cake.
That is a great analogy. The instructions and the execution environment become the exact same thing.
They are isomorphic, yeah.
Yeah.
Which brings up a massive structural problem, I would think.
Memory management.
Exactly. If your code is behaving like a neural network, how does it process strict logic? How does it remember anything without just hallucinating a variable?
Well, that introduces us to Eshkol's memory models. They use an approach called OALR.
Right, which stands for ownership, arena, linear types, reference counting.
It's a serious hybrid of several modern memory management strategies, and it's primarily designed for per-thread arena isolation.
Because when you are doing massive tensor math in parallel across thousands of cores, you cannot have threads waiting in line, locking memory to update a single variable.
Right. Standard locking would completely bottleneck the whole system, so OALR bypasses those bottlenecks.
And they pair that with what they call a core.memory faculty, which is described in the docs as a content-addressed CRDT merged event log.
Now that is a mouthful.
It really is. But I know CRDT stands for conflict-free replicated data type. It's the underlying magic that allows, like, Google Docs to let 50 people type in a document at the exact same time without the whole thing crashing.
Exactly. Now, apply that mechanism to a program's active memory. If thread A wants to multiply a variable and thread B wants to divide it, a normal system would lock, crash, or overwrite.
But with CRDT, Eshkol treats memory as an append-only event log.
Yes, both threads just record their intent to change the value.
And then the mathematical rules of the CRDT guarantee that those parallel realities can safely merge later into a single undeniable truth without ever locking the system.
It's essentially a lock-free parallel reality, and that perfectly sets the stage for the most sci-fi section of the entire repository.
The consciousness engine.
The consciousness engine. It relies on logic programming, active inference, and global workspace theory.
Okay, I have to step in here on behalf of anyone listening. The phrase consciousness engine sounds like pure marketing hype.
It sounds totally ridiculous at first glance.
Right. Is a developer just writing standard logic loops and slapping the word consciousness on it to sound visionary? Or is Eshkol actually attempting neurosymbolic bidirectional integration?
Surprisingly, it is attempting the real deal. They are applying literal cognitive science models directly to code.
Wait, really? How?
Well, take global workspace theory. It's a leading model for human consciousness in neuroscience. It posits that unconscious processes in your brain compete for access to a central workspace.
Like a spotlight in the brain.
Exactly. And the winning information is broadcast to the rest of your brain so you become consciously aware of it. Eshkol implements this programmatically.
So background parallel inferences compete for the main execution thread.
Exactly.
But how does it infer anything? Computers calculate, they don't, infer.
They do in Eshkol, thanks to the type system. The documentation relies heavily on HaTT gradual typing. That stands for Homodopai type theory.
And what does that mean without needing a PhD in theoretical mathematics?
It's actually a beautiful concept. Imagine if you could treat logical statements and computer data types as physical shapes.
Okay, shapes. I'm with you.
Homoto pi type theory essentially says that if two shapes can be continuously bent or stretched into one another without tearing a hole in them, they are mathematically equivalent.
Okay, so it's translating strict true or false logic into spatial geometry.
Exactly. By doing this, the language can mathematically prove that its own logical assertions are sound based purely on their shape.
Wow.
It uses active inference to predict the most optimal path for execution. If its predictions are wrong, it updates its own internal model. It is genuinely reasoning about its own code.
Okay, so let's summarize what we have so far. We have a system that rewrites its own logic into transformer weights, calculates infinite layers of calculus, and mathematically proves its own thoughts using spatial geometry.
Yep, that's Eshkol.
Building a self-differentiating neural computer like that sounds incredibly dangerous if it's just let loose on a server. How does this thing interact with the outside world, and how do they possibly test it?
Containment is a huge focus. This brings us to their agent FFI, the foreign function interface.
Right, because to talk to the world, Eshkol natively supports HTTP clients, embedded databases like SQLite, and subprocess spawning.
But everything operates under a strict capability allow list policy.
So it is sandboxed by default.
Yeah.
The language does not inherently trust its own programs to arbitrarily touch the host operating system.
Right, if you don't explicitly grant it permission to read a folder, it acts like the folder literally doesn't exist.
And that level of paranoia extends deeply into how they test the compiler itself, right?
Yeah.
The quality gates are just staggering.
Oh yeah. Before a release is even considered, it has to pass the SICP completeness report.
SICP being the structure and interpretation of computer programs, the legendary, incredibly dense MIT computer science textbook.
Exactly. Eshkol demands that 100% of the concepts and programs in that textbook are flawlessly executable in their language.
That's a massive flex.
It really is. But that's just the baseline. The real safety net is their 7 pillars of adversarial testing.
Right. These are testing harnesses specifically designed to aggressively break the system.
Yes. They mention P1 through P7 harnesses. This includes standard things like fuzzing.
Which is throwing random garbage data at the runtime to see if it crashes.
Exactly. But they also detail metamorphic property oracles and a depth parametric AD oracle.
Now, most languages just run basic unit tests. You check if input A produces output B. Why does Eshkol need a metamorphic oracle?
Because when a language is dynamically shifting workloads to GPUs and modifying its own logic through a consciousness engine, a traditional unit test is totally useless.
Because the execute path is never the same twice.
Exactly.
Wow.
You can't just check for a static output when the path is constantly evolving. A single tiny mistake in a chain of derivatives could silently corrupt a massive machine learning model.
So what exactly is the mechanism of a metamorphic oracle? How do you test a system like that?
It's like testing a GPS system. If you are building a GPS, you don't need to know the exact distance to every possible destination to know if the software is working.
Okay.
But you do know a mathematical property. If you drive 1 mile south and then 1 mile north, your distance to the destination should be exactly the same as when you started.
Right. And if it's not, the GPS is fundamentally broken.
Precisely. It checks the relationships and the properties, not the specific outputs.
That is a great way to look at it.
Yeah. If the system multiplies a massive tensor by matrix A and then by matrix B, the oracle knows that reversing those operations must yield a specific relational change, regardless of how the JIT compiler optimized the steps in between.
And the depth parametric AD oracle does this while sweeping through massive recursion and numeric depths.
It actively tries to find the absolute breaking point where the mathematical fabric of the language tears.
They aren't treating this like normal software engineering. They're treating it like a high-energy physics experiment.
That is the perfect way to frame it.
They have to build a containment field around the language, hit it with extreme gravity and adversarial math, and just measure if it remains stable.
Exactly. The testing isn't about finding simple bugs, it's about proving physical stability.
So let's pull all of this together for you listening. We started by looking at Eshkol as a wild hybrid.
A very wild hybrid.
It begins its life as a clean, minimalist, scheme-compatible language. But through native mathematical integration, it evolves into an LLVM-powered engine capable of arbitrary order calculus on the fly.
It utilizes lock-free CRDT memory logs to safely run parallel realities.
Right, and it peaks as a neurosymbolic consciousness engine that can map its own instructions into neural network weights.
It represents a profound shift in computing. The overarching takeaway from this documentation is that we are looking at the absolute frontier here.
We really are.
We are moving away from the old paradigm of writing code that uses an AI framework. In Eshkol, the language itself is the AI framework.
The compiler, the math, and the neural inferences are all one unified breathing system.
Exactly.
It really makes you look at the standard tools you use every day a little differently. And that leaves us with a final thought for you to mull over today.
Go for it.
If a system like Eshkol can represent its own operations as transformer weight matrices, and if it actively updates its own models based on the cognitive theory of consciousness, at what point does a programming language stop being a simple tool wielded by a developer?
That's the real question.
At what point does the wrench wake up, realize what it is, and start becoming an autonomous entity that writes itself?
That is the defining question of this next era of computing. And as systems like Eshkol mature, it's an answer we are all going to have to face sooner rather than later.
Definitely. Thanks for joining us on this deep dive. Keep questioning the tools you use, and we'll catch you next time.